Welcome to our educational videos. My name is Anna.
And I'm Peter. In this video, we will focus on the algebraic structure topic in mathematics of cryptography.
To sum up today's lesson, we will explain what algebraic structure is, the relationships and requirements for the common algebraic structures, groups, rings, and fields. After that, we will then learn about a special type of field, Galois fields, as well as its usefulness and applications in the computer world. Then lastly, polynomials. Algebraic structures. Integer sets and certain procedures that are defined for such sets are needed for cryptography. An algebraic structure consists of a set and any operations that are performed on the components of the set. We shall define three typical algebraic structures in this video, namely, groups, rings, and fields. Groups.
A group, G, is a collection of elements that satisfy four conditions and have a binary operation or axioms. A commutative group meets the additional requirement of commutativity. The four conditions that define a group are as follows. Closure. In short, closure means that the result of the operations of two elements in the set is in the set itself. Given that both A and B are members of set G, we can deduce that C, which is calculated by subtracting A and B, is likewise a member of set G. This can specify that the outcome of applying the operations on any two items in the set is another element in the set. This can be the case for any two elements in the set. Associativity. If A, B, and C are elements of G, then operation B in parentheses, operation C is no different to operation in parentheses B. Operation C indicates that it does not matter which sequence the operations on greater than two elements are performed in. This is because it is possible to perform the operations on any combination of the elements. Identity. This property states that for every A and G, there must exist an identity element E and G such that the E operation A is the same with operation E and is the same with A. Inverse. For every A and G, there is also an element in the set called A that is known as the inverse of A. This means A operation inverse of A is the same to inverse of operation A and is the same with the identity element E.
The fifth condition, commutativity, states that, for every pair of elements A and B and G, the equation A operation B is the same with B operation A holds true. If a group meets the following four qualities as well as the extra property of commutativity, then that group is referred to be an abelian group. To make things easier to understand, let's walk through an example. A commutative group or abelian group is a collection of residue integers with the addition operation, noted as G in the set Zn, and an addition operator G, Zn. The components of this set can be added and subtracted without leaving the set. Let us check that using the next slide. Let's fact-check whether or not the group G in Zn with addition operation is a commutative group. First, closure is satisfied since the result of adding two integers in Zn is another integer in Zn. Then, associativity is satisfied, because take 4 plus 3 plus 2 in parentheses is the same with adding 4 and 3 in parentheses then add 2. Next, commutativity is satisfied because 3 added 5 is no difference than 5 added 3. Then, the identity element of addition is 0, so take 3 plus 0 is the same with 0 plus 3 and is equal to 3, which prove the existence of the identity element condition. And lastly, every element has an additive inverse in Zn with an addition operator. For a quick refresher, an inverse of number A in Zn in this case is a which with the addition operator will give you the identity element 0.
Other groups-related applications that will also be good to learn about includes finite group and infinite group, order of a group, and subgroups. So, a group is finite when its set has a finite number of elements. Otherwise, it will be an infinite group. Next is the order of a group. It simply means the number of elements in the group. So if the group is finite, its order is finite and vice versa. Moving on to subgroups, a subset H of a group G is a subgroup of G if H itself is a group with respect to the operation in G. This will make more sense once we go into examples right after this slide, but before that, it's necessary to mention cyclic subgroups. And, basically, if a subgroup of a group can be generated using the power of an element, the group is cyclic. From there we have cyclic groups, which is a group that is its own cyclic subgroup.
To make sense of what we have discussed previously, here are some examples. Example 1 is, H, Z10, a subgroup of G, Z12? The answer is no. Why? Because although H is a subset of G, the operation in H is in modulo 10 and G is in modulo 12. Thus, H itself is not a group with respect to the operation in G. Example 2. Find cyclic subgroups for GZ6. First of all, Z6 has 6 elements ranging from 0 to 5, and from there we will have the following subgroups. The cyclic subgroup generated from 0 is H1, which has only one element, which is the identity element 0. The cyclic subgroup generated from 1 is H4, which is G itself. The cyclic subgroup generated from 2 is H2, which has 3 elements 0, 2, and 4. The cyclic subgroup generated from 3 is H3, which has 2 elements 0 and 3. The cyclic subgroup generated from 4 is H2. This is not a new subgroup. The cyclic subgroup generated from 5 is H4, which is also not a new subgroup and is G itself. So in total there are only 4 subgroups for G in Z6 and addition operation. Before moving to other sections, there are 2 other applications of groups that we need to familiarize ourselves with, and they are the Lagrange's theorem and order of an element. Lagrange's theorem: assume that G is a group, and H is a subgroup of G, then, based on this theorem, the order of H divides the order of G. Order of an element: the order of an element is the order of the cyclic group it generates. In short, the order of element, A in G, means, a repeating by n times with n being the smallest integer, will equal E, or the identity element with respect to the operation in G. Then again, we will also make these concepts make sense with a couple examples. First example, let's find the orders of the elements in GZ6. To begin, as mentioned, we know that the order of element, A in G, means A, repeated by n times with n being the smallest integer, will equal E, or the identity element, which is 0 for addition, and 1 for multiplication operation. So we will ask ourselves, how many times will 0 need to repeat itself in modulo 6 to equal to 0? The answer is 1 time only. Similarly, with 1, we will need to repeat adding 1 6 times, so 1 plus 1 plus 1 plus 1 plus 1 plus 1 to get 6, then modulo 6 and get 0. Let's repeat this process with 5. We will have to keep adding 5 for 6 times, so that once at modulo 6, we will get 0. By doing so, we found ourselves the orders of elements in G. Moving on, we will find the orders of the elements in GZ10*, multiplication. This is trickier because the set only has 4 elements, 1, 3, 7, and 9, so its order equals to 4. In this case, we have the identity element equals 1 and our operation is multiplication. So, with 1, we will have to multiply it 1 time to get 1 in modulo 10. Similarly, repeat the process with 7. We will need to repeat the operation 4 times, so 7 multiply 7 multiply 7 multiply 7 to get 2401, then modulo 10, we will get 1, which is our identity element in this case. After we walked through these examples, hopefully you are ready to continue with the next section: rings.
A ring is an algebraic structure with 2 operations. The first operation must satisfy all the 5 properties required for an abelian group, which are the closure, associativity, commutativity, existence of identity, and existence of an inverse. The second operation has to satisfy the closure property, associativity property, plus the distributivity property, meaning the second operation has to be distributed over the first operation. Commutative ring. A commutative ring is a ring that satisfies the commutative property. A set Z with 2 operations, addition and multiplication, satisfies the properties of a commutative ring. Only 3 of the 5 characteristics are satisfied by the multiplication operation, but all 5 properties are satisfied by the addition operation.
A field is a commutative ring. A set is considered to be a field when the only 2 binary operations that can be performed on the set are addition and multiplication. If the first set satisfies all the 5 properties and the second set satisfies all 5, but the identity of element of the first operation has no inverse with respect to the second, then it is considered to be a field. In this section, we'll be discussing Galois field. Galois showed that for a field to be finite, the number of elements should be p raised to the power n, where p is a prime and n is a positive integer. A Galois field, GFPn, is a finite field with pn elements. A very common field in this category is GF2 with the set 0, 1, and 2 operations, addition and multiplication.
An example of GF of 2 with the addition and multiplication operations are as shown below. The set only has two elements, which are 0 and 1. Now that we know what the elements are, we will proceed to add 0 and 1, to 0 and 1, in modulo 2, in order to determine the additive inverse. We will do same by multiplying 0 and 1, in modulo 2 and then calculate the multiplicative inverse. The elements all have an additive inverse, and only 0 doesn't have a multiplicative inverse. This satisfies the properties of a field. Next on the presentation, we'll be talking about polynomials.
Polynomials are essential for ensuring that security is provided. Polynomials are valuable in cryptography for a number of intuitive reasons, including their ability to succinctly encode a lot of data. But first of all, why do we convert from binary to polynomials? Computer hardware processes polynomials faster. A polynomial of degree n-1 is an expression of the form, where xi is called the height term and ai is called coefficient of the height term. An 8-bit word can be represented by a polynomial. The n-bit, for example 1001111001, is represented in polynomials as x raised to the power 7 plus x raised to the power 4 plus x raised to the power 3 plus 1. This can be calculated by using the above f of x expression.
Addition of two polynomials never creates a polynomial out of the set. However, multiplication of two polynomials may create a polynomial with degrees more than n-1. This means we need to divide the result by a modulus and keep only the remainder, as we did in modular arithmetic.
For the sets of polynomials in GF2 raised to power n, a group of polynomials of degree n is defined as the modulus.
The modulus in this case acts as a prime polynomial, which means that no polynomials in the set can divide this polynomial. A prime polynomial cannot be factored into a polynomial with degree of less than n. Such polynomials are referred to as irreducible polynomials. The examples of them from the degree 1 to 5 are as shown in the table here. Moving on to the operations in polynomials, addition and subtraction operations on polynomials are the same operation. Let's take a closer look at this example calculating x to the power of 5 plus x to the power of 2 plus x to the power of 3 plus x to the power of 2 plus 1. Before we calculate it, it will make our job easier to list the polynomials by degrees and lines. You can see here we line up x to the power of 7 together in a line and power 6 and so on in their line. To calculate them, keep the uncommon terms and delete the common terms. In other x raised to the power of 5, x raised to the power of 3, x, and 1 are kept in x raised to the power of 2, which is common in the two polynomials, is deleted. Multiplication in polynomials is the sum of the multiplication of each term of the first polynomial with each term of the second polynomial. However, we need to remember 3 points. First, the coefficient multiplication is done in GF2. Second, multiplying x raised to the power I by x raised to the power j results in x raised to the power of I plus j. Third, the multiplication may create terms with degree more than n-1, which means the result needs to be reduced using a modulus polynomial. Again, to make it clear, let's walk through one example. To calculate x to the power of 5 plus x to the power of 2 plus x times x to the power of 7 plus x to the power of 4 plus x to the power of 3 plus x to the power of 2 plus x. We first multiply the two polynomials as we have learned in algebra. Note that in this process, a pair of terms with equal power of x are deleted. For example, x to the power of 9 plus x to the power of 9 is totally deleted, because the result is a zero polynomial, as we discussed before. However, since the power 12 is over the power 8, and we are in GF2, to the power of 8, thus, to find the final result, divide the polynomial of degree 12 by the polynomial of degree 8, the modulus, and keep only the remainder. The division process is the same as we have learned in algebra, but we need to remember that subtraction is the same as addition here. To get from power 12 to 8, you need to reduce it by x raised to the power of 4. We then multiply x raised to the power of 4 by x raised to the power of 8 plus x raised to the power of 4 plus x raised to the power of 3 plus x plus 1. We get x to the power of 12 plus x raised to the power of 8, plus x to the power of 7, plus x to the power of 5, plus x to the power of 4, subtract them from x raised to 12, plus x raised to 7, plus x raised to 2, we get x raised to 8, plus x raised to 5, plus x raised to 4, plus x raised to 2. From there, we can still divide it by x to the power of 8, plus x to the power of 4, plus x to the power of 3, plus x plus 1, one more time to get 1, and do our subtraction thing to cross out the common elements and keep the uncommon 1 to get the remainder. We get our result of x to the power of 5, plus x to the power of 3, plus x to the power of 2, plus x plus 1, by multiplying x to the power of 5, plus x to the power of 2 plus x, by x to the power of 7, plus x to the power of 4, plus x to the power of 3, plus x to the power of 2 plus x. And that concludes our lecture today on algebraic structures in cryptography. We hope you found the lecture interesting, and as usual, remember to come back for upcoming interesting content. Thank you and see you next time.